Hello, everyone, and welcome to today's webinar titled Overcoming Challenges in Maritime PNT Applications. My name is Khalid Abdallah, and I am the Sales Success Manager at Calian. While I have your attention, and before I kick things off, I'm going to cover a few housekeeping items. As we are going through the webinar today, feel free to use the question box in the webinar panel to ask questions as they come to you, and we will address as many as possible at the end. This webinar is being recorded, and you will be added to our webinar library in our resource center on the Calian website. We will email out the link to the recording within the next few days. Make sure to stay tuned to the end as for your questions. So I'm really excited for today's webinar. We have an outstanding lineup of speakers, each bringing a wealth of experience and expertise in the GNSS field in marine applications. I'm joined today by Dennis Baumholt, Operations Manager at Trelleborg, my colleague, Joseph Botros, Application Engineer at Calian, Ben Dean, Senior Manager, CNAV Positioning Solutions at Oceaneering, and I'll be your host today. For today's agenda, we will go through a welcome and introduction. The purpose of today's session is to provide you with valuable insight into GNSS marine applications. We'll begin with welcome introductions. Ben will do an overview of marine applications and challenges. Joe is going to address how to overcome these challenges, and Dennis will discuss the Panama Canal use case. Calian is a public company formed more than 40 years ago in Ottawa. The company currently has 5,000 employees across 5 continents. Calian has 4 divisions: Advanced Technologies, Health, Learning and IT, and Cyber Solutions. Calian GNSS falls under the Advanced Solution division. Calian GNSS was established in 2009 as Talisman Wireless, acquired in 2020 by Calian. We are a leading manufacturer of GNSS antennas and accessories. Our antennas are Canadian made. We also offer engineering services such as antenna customization and tuning. We are known for our quick fulfillment, high quality support, technical guidance, and technology. So without further ado, I will move it to Ben.
Thank you, Khaled. So today I'm just going to give a short presentation. I'll give a brief overview of who Oceaneering are, what we're doing in the marine sector for PNT, and some of the challenges we see in the PNT market with some of our customers. So just a brief background on myself. I graduated from the University of Nottingham with a Bachelor of Science degree in Survey and Mapping Science almost 20 years ago. I worked offshore as an offshore surveyor, online surveyor, on offshore energy construction vessels, laying pipelines and infrastructure. And then I joined a company called CNC Technologies, which was later acquired by Oceaneering. Within CNC Technologies, Oceaneering resides the CNAV positioning group. And during my time with Oceaneering, I obtained my master's degree in GNSS from the University of Nottingham. All right, so I'll just give you a brief background on Oceaneering. So we celebrated our 60th anniversary last year. We started in 1964 as a small diving company, which later merged in 1969 and became Oceaneering International. We then transformed into a multinational global engineering company, and today we develop products and services for use throughout the life cycle, mainly in the offshore oil field, from anything from drilling to decommissioning. We also operate the world's largest premier fleet of robotic vehicles, ROVs. We also serve other sectors such as aerospace, defense, and theme park industries. And today we turn over $2 billion in USD. Now this overview gives a good snapshot of all the touch points we're working at through the life cycle of the offshore oil field. At the top there, you'll see CNAV positioning solutions, and that's the sector we're going to present today. And we'll move on to just a quick background on CNAV. So we started over 25 years ago in the positioning business through the first pioneer to launch what we know as a PPP service, so precise point positioning. So some may ask, what is GNSS augmentation? So as I said, 25 years ago, or more than that, in 1997, a new absolute positioning technique was developed, which eliminated the reliance on real-time shared data with base stations. So traditionally we'd use real-time data with base stations. Now PPP uses base stations, not in their same sense of being a relative positioning. So we have a selection of base stations around the world, and we calculate precise orbits and clocks to correct the broadcast orbits and the minor clock errors in each of the GNSS satellites. So today, and 4 years ago, we transitioned from delivering these corrections to our end users from Inmarsat, and we now deliver exclusively over the Iridium communications infrastructure. So we basically calculate a precise orbit and clock, use dual frequency GNSS receivers, and allows all of our end users to position themselves to less than a few centimeters anywhere on the Earth, pole to pole. So now we're going to see what applications or what end users do we have that have a requirement for the CNAV LEO GNSS augmentation services. So really, our customer base is split into two types of application. Those require repeatability and stability, and we'll see that in a second, and those that require hierarchy. So customers that require repeatability and stability are those marine users and marine vessels that will have a system installed known as dynamic positioning, or DP. So again, for those that aren't familiar with what dynamic positioning is, dynamic positioning is a computer-controlled system on a vessel which allows a vessel to maintain a vessel's position and heading using its own thrusters. It will use positioning references such as GPS, and these are one of the primary position references, but also combines these with wind, motion, gyro compasses, etc., to allow the vessel to maintain station. Vessels can range in size from anywhere from a 30-meter FSIV, so field service intervention vessel, crew transfer vessel, anywhere up to a 400-meter drilling vessel or pipeline installation vessel. The DP variants can vary in classifications from DP1, DP2, DP3, and this is down to the level of redundancy each of the vessels has. You can see from the previous picture that reliability and stability is key. You know, these vessels can be operating, they can be attached to the seabed through a drilling pipe. So obviously maintaining position is very critical to the safety of that drilling rig. They can be delivering pipe or materials to the rig, and often when offloading to the rig's crane, you could be within 2 or 3 meters of the rig, sometimes with heavy masking and shading. With modern GNSS, you still have a lot of satellites, but it's something to bear in mind. But again, this is where criticality and redundancy, availability of the signal is of utmost importance. So let's move on to have a look at the other application that mainly we see in the need for GNSS augmentation, and that's for survey and positioning. Again, that can range from positioning of a rig, positioning of a pipeline, pre-existing installation of pipeline, etc., etc. You can see here our DRIX vehicle under the surface. You can see our Freedom AUV, and obviously here we're doing pipeline survey, and the DRIX vehicle is tracking the Freedom vehicle. But again, users using for survey are very interested in accuracy. We're mapping the seabed to the highest accuracy we can. So GNSS is a key part of that. It feeds into the error budget, feeds into the multi-beam budget, IMU budget, all that kind of thing. So the more accurate the position at the surface, the more accurate the seabed mapping is going to be. So with that, let's move on to see some of the challenges that we see within these applications. So commonly, and pretty, this is a daily thing we see within our customer base, is interference, both in band and out of band. On the next slide, I'll highlight some of the typical communications devices we see on a rig. So you'll see in the photograph there, SATCOM domes of various types. You'll see a typical mast view from a small PSV, very cramped, full of many different types of communications devices, Iridium, Inmarsat, VSAT, Starlink, OneWeb, radars, you name it, it's got it on there, and space is at a premium. Everyone is fighting for a space in that scenario. GNSS and Iridium C, GMDSS and GNSS for DP should always take the priority on a vessel, given their criticality, but that's not always the case, as we'll see. Often vessels will get many new devices retrofitted. More and more crew require connectivity to the shore, as we YouTube Gen Z generation, and obviously connectivity, client connectivity, sending data back to the shore. More and more devices are retrofitted every time the vessel comes into port. So you can see where these kind of things are a challenge. In the bottom left, you'll see a typical plot we may see, and again, we may see this on a support ticket weekly, if not daily. So you'll see a delta plot in delta X, delta Y, delta Z from the reported mean position or from the starting position, and you'll see 3 occurrences there of some kind of interferer, which is making the position for a DP aspect and a survey aspect unusable. So what can we do to mitigate some of those sources of interference in the marine? We jump to the next slide. So Calian developed the Veristar range and then expanded that further with the Veristar VSP6037L, which has the advanced marine filtering. So that has out of band rejection in areas where overlapping devices will be transmitting, such as Inmarsat C and Iridium. Now, it's quite interesting because 10 years ago or 12 years ago, this was never really an issue. Interference was not as much of a common issue. And back then, we were only, or GNSS devices were only capable of receiving GPS, and we were only transmitting precise clock and orbits mainly for GPS. Obviously, with the advance of GLONASS, that became the second well-used constellation, then Baidu, Galileo, which obviously opened up the number of frequencies we were using. Specifically GLONASS, who chose to obviously use a completely or a higher frequency than everyone else. We introduced GLONASS into our solution and immediately began seeing issues because of the older antenna technology, no specific filtering to mitigate against interference, and that's kind of how a lot of these products like the Veristar were born out of that. And I say they do a very good job today. We see less and less issues. Still, you may see issues mainly down to power or faulty devices, but this is the de facto antenna solution or filtering, marine filtering we use on all of our offshore installations. And I know Joseph will give a more detailed overview of this product in his upcoming slide deck. Other things we see, and often a bit more difficult to always detect to understand if you are being jammed, but jamming is becoming more prevalent these days. We see in certain geopolitical areas. So on the upper left, this is the Eastern Mediterranean, Black Sea, Red Sea. Now, this data isn't true of a marine interference. This is collected from aircraft anti-collision avoidance systems, ADS information, but you can still see this is just a snapshot of 1 day of aircraft reporting suspected jamming. So you can see the prevalence of jamming. Zooming in a little bit on the Black Sea area, you'll see a number of blocks which are currently active and being drilled for oil, and the number of offshore service vessels and rigs. So what do we recommend in those areas? We can see on the next slide, there's another product within the Calian portfolio, So the lower elevation angle nulling antenna. So this creates a null, an elevation angle of 0 through to approximately 15 degrees, which will attenuate and mitigate up to a 600-watt jamming signal broadcast from an angle of 10 degrees. So again, Joseph will give a more detailed overview of the XF filtering and the new XF Plus filtering, plus some other new exciting technology that will be available later in the year. So with that, thank you very much. I'll hand over to Joseph, as I mentioned, and he'll give a more detailed overview of the challenges we see in the marine PNT sector and some of the products within the Calian portfolio that can be used to mitigate some of these threats and some of these issues that we see. Thank you.
Thank you, Ben. And hello, everyone. I am Joseph Botros, Field Applications Engineer at Calian, talking to you today about GNSS antenna design considerations specifically for maritime environments, where unique challenges like interference, environmental stress, and multipath affect performance. First, a little bit about me. I received my bachelor degree in engineering physics with the highest distinction, and followed that with a master's degree in electrical engineering, where I got acquainted to Ben Talisman. I've been with the company for 7 years, starting off as an intern, then an antenna designer, senior designer, and then field applications engineer, my current role. As Ben discussed in his section, unique challenges like interference, environmental stress, and multipath are prevalent challenges in the marine environment. So let's take a deep dive into each of these and discuss how Calian offers solutions. Maritime GNSS faces 3 big challenges: multipath, interference, and harsh environments. Low axial ratio across elevation can help reduce reflections and keep signal qualities high. That's a solution for multipath. Our XF filtering reduces out-of-band interference, and rugged enclosures protect against marine stresses. So let's dive into each one of these. First, let's explore how a great antenna tackles multipath challenges. At sea, signals can reflect off all sorts of structures. You've got the structures of the ship, nearby structures, cargo containers, and even the ocean surface. And this can cause multipath delays. So imagine you have a reflected signal that comes in, a GNSS signal that comes in, it reflects off something, changes its polarization or the way it rotates, and it's because of the reflection, its path is extended, hence the delay. So to mitigate this, having proper antenna placement is important, but the antenna design is even more critical. Specifically, having low axial ratio and high gain at low elevations can be key designs to reduce sensitivity to multipath. GNSS receivers, of course, are very critical in multipath mitigation, but of course, the antenna is the first line of defense. It is the first component. It starts at the antenna. So let's first walk through how to interpret a radiation pattern, focusing specifically on polarization and multipath projection. First, we know that the GNSS signals are transmitted in right-hand circular polarized, or RHCP. However, when a GNSS signal reflects off a surface, waters, ship structures, cargo, the polarization flips and no longer travels in the right-hand polarization, but rather in the left-hand circularly polarized. So RHCP gain, that is the wanted direct GNSS signals. You want the antenna to be as sensitive as possible. That is the curves in black. And the LHCP gain, which are the curves in red, you want to reduce that as much as possible because you want an antenna that is not sensitive to the unwanted reflected signals. And the axial ratio is related to the difference between these two. Low axial ratio means stronger right-hand circular polarized signal and weaker left-hand circular polarized reception, which is exactly what we want. So minimizing the antenna's LHCP sensitivity through having a low axial ratio over the entire upper hemisphere is critical to rejecting multipath interference. Our Veristar element addresses this challenge. Special curved pedal design. So the special curved pedal design ensures low axial ratio, even at low elevation angle. So you can see here how at horizon, the axial ratio is less than 3 dBs over the entire GNSS spectrum. And this is quite a feat. most of the time we consider that achieving 3 dBs at zenith for aspect ratio is the standard. So having 3 dBs at horizon, amazing. The Veristar antenna also offers high gain at low elevation. The benefits of this is stronger reception from satellites that are sort of at the horizon. This improves reliability in tougher environments, like in open oceans, or if you imagine if a ship's going through this patch of ocean where there's a lot of waves and the ship's bouncing up and down, well, that antenna is also doing that same motion. So having really good gain over the whole sky view will help keep it tracking those GNSS signals. To the left, you can see a comparison of our Veristar to the Veriphase's right-hand circular polarized gains. Here, the Veristar is compared to the Accutana patch. So we continue to see the high low elevation gain advantages of the Veristar. But as a short disclaimer, it is good to note that having low gain at low elevation, or high gain at low elevation, sorry, can have a downside. And that is more sensitivity to low elevation noise. So not just the GNSS signals, but could be anything else that's coming from there, like what we're about to see next. All right. Now we'll cover how to solve interference challenges. So satellite communication transmissions, such as, so from onboard electronics, such as Iridium and Inmarsat antennas, are actually common sources of interference. So you've got the Iridium uplink from 1621 to 1626 megahertz, Inmarsat uplink 1626 to 1660 megahertz, and consider that this frequency range is it's uncomfortably close to the GLONASS G1 frequency range up to 1606 megahertz. So that's almost co-located in frequency, and that could be a pretty substantial source of interference in the maritime space. So the solution to this, sharp targeted filtering that provides overall high out-of-band rejection at 1621 megahertz and beyond. And we call that marine filtering. So the Veristar incorporates a variation of the extended filtering technology that specifically does the following. So it has sharp targeted filtering, as we see here in this plot, and strong out-of-band rejection up to about 100 dBs while maintaining good in-band GNSS performance. So here in the plot, you see the red, that is our standard XF filtering. Now with the marine filtering, we get additional rejection to reject the Iridium uplink, including and also the Inmarsat uplink to the levels that you see in the plot. So the marine is shown in blue and the standard XF is shown in red. Finally, let's cover how to solve environmental challenges. So beyond RF issues, the marine environment itself is quite punishing. You can imagine salt spray that brings a risk of corrosion, water that could cause flooding of the antenna's internals and water ingression, and fog and mist could bring about moisture-related failures. So how do we solve salt spray challenges? The antennas, they're designed using a thick, high-grade plastic and corrosion-resistant metal parts. So you'll notice here in the images, the TNC connector, the RF connector, and that little pole mount insert, they're made of material that are more corrosion-resistant than the standard materials. Now, how do you solve water challenges? The antennas are IP69K rated, and this is the highest level of waterproofing on the IP scale. So we accomplish this through the highly engineered enclosure with seals, O-rings, and gaskets at very strategic points where the plastic has these openings. So you notice the seal between the radome and the base, all those little holes for the screws, and the TNC connector and the inserts, they are all protected. Finally, for fog and mist, well, the antenna is rated at IP69K. However, the connector to cable interface is still the responsibility of the user, and it should be waterproofed. This is quite important. There is a Calian guide that is available to help with this. So as an overall solution, the Veristar, it stands out, and this is why it is the basis of our marine antenna, the VSP6037L-MAR. That is the star of this webinar. In addition to its excellent multipath mitigation, its marine filtering, and robust enclosure, it has very tight phase center variation, full band coverage, strong low elevation gain, and world-class L-band correction reception and high latitudes. So you can imagine if you're in Scandinavia or in the Arctic and you rely on these corrections from these geostationary satellites. So that's corrections over the L-band frequencies. Well, those satellites, because they're geostationary, they're parked sort of at the equator, they'll be quite low at the horizon. So having an antenna with high low elevation gain is quite an advantage for those particular applications. However, as we mentioned before, well, there are instances where having high gain and low elevation is actually not good. It's detrimental. And one of those instances is where intentional interference or jamming is present at the ground level. So you could imagine if you're talking about, say, traversing in the Baltic Sea, Black Sea, the Eastern Mediterranean, there are going to be instances where there will be interference sort of at the horizon level, sort of at the you're traveling at the periphery of these what I can call hostile zones, I would say. So the solution we present to that is the AJ977XF Plus, and then Ben was describing a little bit about this antenna. So the XF Plus, what that is, it's our XF technology, which includes pre-filters, tight pre-filters, several additional stages of filters, and the XF Plus, the plus part, is the upper and the lower band. The upper and the lower GNSS band, they are separate from the input of the antenna, the input of the LNA to the output of the LNA. The paths are completely separate. The advantage of that is if the L1 is being jammed, then the L2 can be less affected and can continue to produce usable signals, and vice versa. So the AJ977XF Plus, it is a low elevation angle nulling antenna designed to reject horizon level interference and enhance positioning reliability in difficult waters. So this is done by creating a null, as Ben was describing, 0 degrees, 15 degrees, and it is a useful tool in marine applications where the vessel is operating in these places where you would expect to get these sources of interference. So the AJ977XF Plus, it offers protection in what I like to say the spatial, spectral, and saturation domains. That means the spatial, it's got the null near horizon, spectral, the XF Plus filtering, and saturation domain. So the output linearity of the antenna is quite high, so that gives a little bit of headroom in case the signal does end up getting through, the jamming signal gets through. So this is the really exciting part. Our upcoming CR8894 PXF Plus. This is a controlled reception pattern antenna, or SERPA. It provides spatial awareness by forming up to 3 dynamic nulls per band. The upper band has 3 nulls, lower band has 3 nulls. So it not only rejects interference, but it also helps identify and approximate the direction of jammers in real time. So you'd ask, what is the difference between this and the AJ? The AJ, it's a fixed pattern, FERPA, fixed reception pattern antenna, and this is a SERPA, controlled reception pattern antenna. So the FERPA, it's static. This is dynamic, so it could steer those nulls in the direction of the jammer and sort of track them as the SERPA or the jammers are moving. The design includes marine filtering, and it features compact, lightweight, low power, and corrosion-resistant plastic enclosure. So it is purpose-built for resilient maritime operations. We took everything we learned on the Veristar marine antenna, and we're applying it to this new SERPA. All right, so as we push the limits of positioning resilience at sea, it's now time to hear from Dennis at Trelleborg, where cutting-edge marine solutions meet real-time, real-world challenges. Thank you.
Yeah, hi. My name is Dennis. I work with Trelleborg Marine Systems, and I've been doing that for the past 29 years. Trelleborg acquired Merrimatic in 2018. I started at Merrimatic, obviously, and since then we have been solely focusing on navigation and piloting solutions. I started in '95, and back then we did hydrographic products like echo sounders, side scan sonars, tide gauges. We had a complete survey package that we delivered to clients around the world. And my first encounter with GNSS was installing Novotel ProPack on a dredger in Kokkola in Finland. Since then, I've been developing our portable piloting units, and the first PPU we delivered in 1999. A few years back, I became operations manager, and I've been doing that ever since, and left the development for younger and more clever people. I enjoy playing table tennis and paddle in my spare time, and I enjoy life with my wife and 2 kids. Yeah, and I'll give you a quick overview of our company, an introduction to Trelleborg and our navigation and piloting solutions. I'll show you our products, and finally I will tell you a little bit about our Panama project, and then a bit about Trelleborg. Trelleborg is the world leader in engineered polymer solutions. Sales exceeding 3 billion euros. We have a footprint in nearly 40 countries, backed by over 100 manufacturing sites and 30 research and development centers. And our diversified portfolio serves industries ranging from aerospace and automotive niche to medical and diversified industrials. Our strategic balance of geography and industry focus has made us a trusted partner worldwide, ensuring that wherever there's a need for advanced polymer solutions, Trelleborg will be there. And yeah, how do we come into this business of polymer and rubber stuff? We are part of the business unit called Marine and Infrastructure, and the way that we came into this industry is because they make marine fenders, and then they have taken over a lot of businesses within the industry going on in the port. We are approximately 1,200 people employed in marine and infrastructure. Within marine and infrastructure, there are 5 groups. Navigation and piloting is one of them. We have 40 people employed. Our salespeople are placed around the world where the clients are. The majority of our staff are hardware and software developers. And we are the global leader within our field, and yeah, do business all over the world, US being our largest market. Our clients are pilots, tug operators, ports, and so on. And all these professionals, they need situational awareness wherever they do the job. And yeah, our primary group of clients are marine pilots. And yeah, the pilot's job is to ensure a safe transit within the port or confined waters. They have local knowledge, and they primarily navigate by eye, but pilots, since the vessels grow bigger, the ports does not grow bigger, they need some kind of technology to assist them to make the right decisions. So that's where we come into the picture. We develop the portable piloting units. They are small, very portable, easy to carry on board. And as you see, this pilot is climbing a ladder on the side of the ship in even rough weather. The sun is shining, everything is nice here, but imagine going on board a ship at high sea. The infrastructure does not grow as fast as the size of the ship. You see this vessel, it's getting into a port. It cannot do anything itself. It's got a propeller in the back. Going into the port, it needs tug assistance and positioning the vessel in order to give commands to the tug operators requires accurate positioning and reliable positioning, and that's where we get into the picture. We provide a system consisting of positioning devices, positioning sensors, and software. And we have an example here with a bird's eye view of a vessel going into a dry dock, giving distances to the wall of the lock. And we have a look at different applications. You see some predicting where the ship is going to be over time, giving distances along a route, distance measurements, speed measurements toward a terminal or jetty. And also we have very accurate sea charts providing accurate underkeel clearance. We have a wide range of products. We have a very simple product like the CAT ROT, just taking data from the vessel itself, very unreliable data. Therefore, we have another device giving accurate position, speed, and course that you can add to this solution. So that's the lowest end of our product range. Then we move up to the CAT Pro, which is completely independent. It will provide position, speed, course, heading, rate of turn, and which is all that a pilot needs to do the job. Then at the end, we have the CAT Max, which is the high-end solution, adding AIS information, even a UHF radio is built in, so that several vessels can communicate between one another. All of these devices do RTK positioning, the CAT Max through UHF or NTRIP, and the other range through NTRIP or internet-based corrections. All these products are the portable units that we do. Then we have the story about the Panama Canal. They've been our clients for more than 10 years. They have been using a wide range of our products since they built the new locks called the Neo Panamax locks. They have got the idea to have an independent system. So in the Panama Canal, they have two different sets of locks. The Panamax locks, which is where the small vessels transit. They are pulled by locomotives. The maximum beam is 106 feet. Those vessels are relatively small and can easily be handled by locomotives, but through the Neo Panamax locks, the beam, they can take vessels up to a beam of 168 feet. And these locks today carry more than 50% of the cargo going through the canal. They were taken in use like 10 years ago and are handled by tugboats. So these vessels need very accurate positioning, since you see on this picture there's a very little space between the vessel and the door and the lock walls. The vessels, they transit through the canal. They are lifted 27 meters above the sea level through 3 different sets of locks, and we provide them with the very accurate positioning and also a complete system where they have a good overview of all the traffic. So the Panama Canal got the idea to have a fixed install system installed on the vessels, since they had a lot of logistic issues having equipment available at the Atlantic and Pacific side. This would make the job much easier and more efficient. So the conventional way of pilotage through the canal was to have the portable system picked up. It was set up on the vessel by a boarding crew. Then the pilot boarded the vessel, came on with his iPad connected to the system, and he did the pilotage. Then a boarding crew came on board, took down the system, brought it to the workshop for maintenance and charging, and then eventually at the end it was transported to either the Atlantic or the Pacific side. The new system and the new way they do it, the first time the vessel comes to the Panama Canal, the system is calibrated, and then the pilot goes on board, have very high accurate system installed already, just connects to it, do the pilotage, say goodbye, and the pilotage is over. It sounds very easy. It's a tough job the pilot does. So, but from the technical point of view, this is an excellent solution. If we have a look at the system that we provide, so basically it is the CAT Max permanently installed, all in a box with everything in it. We deliver it with GNSS antennas, VHF, UHF antennas, cables, tool for terminating the cables, and everything that goes with it. Even an iPad with an app that the captain can use in any port that he attends. And also another important thing to mention here is that the system can be used in any port around the world by any pilot, so they can connect to the system and get data from this system, and thereby have a good and reliable positioning system. Yeah, and of course the CAT Max, one important feature I already mentioned, that we have that it does accurate positioning. It's got a battery in case of a blackout on the vessel, so the system will keep working. It supports all GNSS systems, dual frequency. It detects spoofing and jamming, and it's got a built-in IMU as a backup. So it ensures a safe passage through the canal. So what challenges do we face? It's very similar to what Ben sees in his kind of business as well. There's a lot of stuff up on the compass deck. So finding a good location for the antenna with a clear view to the sky, that's a challenge. Then, first of all, a view to the sky, but then multipath comes into the picture. There's a lot of obstructions nearby. So Khaled, if you move to the next slide, then we see the antenna, a nice antenna installed on a railing. There's a light, searchlight, there's a lamp, there's all kind of stuff nearby, and we need to be able to avoid being affected by reflections from these sources. So having more GNSS signals and systems available, of course, help on this, but the antenna itself is key. Furthermore, interference, Ben also mentioned this, there's a lot of systems installed up there transmitting, and that causes interference. So again, a good location of the antenna far away from these emitting sources, and also the antenna filters, very important. Spoofing and jamming, again, tracking more systems, definitely help on this. An anti-jamming antenna would be nice. In our case, it's not really possible. And then, of course, we have an IMU installed that will help. First of all, it can give a warning if the movement differs, and also it can take over in case of dead reckoning. So we use both OEM and the boxed antenna from Calian, and having those with a proper ground plane in our systems really does the job. So yeah, we're very happy with the performance of these antennas. Back in the days when we started developing our PPUs, we used other antennas, smaller antennas. Of course, you want the smallest antenna possible, but we came to the conclusion that antenna is one of the most important parts in our system, so we don't go on compromise with that. I can recommend that when you start to design something, and we're very happy with the performance of the antennas that we are using. That's about it from me, so I guess back to Khaled for any questions available.
Thank you, Dennis. Thank you, everyone, for your time and for the valuable information shared on today's webinar. We move into the question and answer session. If you have any questions, as stated in the beginning of the webinar, there is a question box in the tools there. The first question coming in is, can you please clarify a bit more about S3 protection?
Sure. I can take that one, Khaled. Thank you.
Thank you, Joe.
So, that's a great question. So S cubed is really just a term to specify that it's providing protection in 3 different senses. It's just a little bit of a marketing flair to it. So spatial as in like SPATIAL, that's in the space domain. So that is the nulling performance of the AJ977XF. Spectral, as in this frequency domain. So in the frequency domain, you're seeing the filtering of the LNA. So it's the protection granted from the XF technology, and saturation. So that is, if you look at the chain of the LNA, you have multiple stages of filtering and amplification. Typically what happens is if you have a really high power signal, it could continue to go through from the antenna to the LNA into each of those stages, and it could saturate the output stage. And when that happens, well, all bets are off. there's no GNSS signal is going to be able to be received from the antenna. So we offer a little bit of a boosted output stage. We have a little bit of more, it's more so on the EJ977XF, not the Plus, but it's higher currents for the output stage, which allows us to get a higher output linearity. That means we have a bit more headroom, so that if a high power signal does go through, there's a little more, it could be higher power before it starts to saturate. So that's what we mean by S-cubed: spatial, spectral, and saturation.
Excellent. Thank you, Joe. Question number 2. If very tight filters are used, including before any gain stages for mitigating SATCOM interference, wouldn't that degrade the performance of the LNA significantly, like higher noise figure? How do you deal with that?
I guess I'll take this one as well. I'll quickly mention that is a really good point. You could consider that because we are adding pre-filters before any amplification, that the insertion loss will be quite high, the noise figure will be quite high. So, well, we do have a very careful and specific selection of those pre-filters. We make sure the insertion loss is about a dB, maybe less, just around a dB at the frequencies of interest. That way, the noise figure is actually marginally increasing, could increase by half a dB to a dB compared to a non-pre-filtered filter. Sorry, it could increase by, it would be half a dB compared to, say, a pre-filtered antenna, or maybe 1 or a little bit more dB compared to a non-pre-filtered antenna. So while the noise figure is increasing, overall, because there is a lot of margin in the link margin, it doesn't have that big of an effect on the overall performance. And it's actually an advantage because you are rejecting, from the get-go, you're rejecting those out-of-band signals before they're amplified by the first stage.
Thank you, Joe. Dennis, we have a question for you. Is CatMax installed all the time on the vessel, or is only used by pilot and temporarily installed on the vessel?
Yeah, so the CatMax is the portable system that we have. So that one is not permanently installed. It's carried by the pilot typically on board the vessel and installed during the transit. We have other systems like the P3 system, which is a permanently installed system for a vessel. Similar systems we supply for work boats, for tugboats and other vessels that requires more permanent positioning. Common for them all is that they do a position, speed, course, heading, rate of turn. They receive AIS, so they provide all this data on a Wi-Fi signal or on a cable to other systems on board the vessel, or both at the same time. But our applications run on an iPad wirelessly, so they can carry the iPad to anywhere within the bridge or the wheelhouse.
Great, thank you, Dennis. Joe, I think this one's for you. Does Calian antenna serve as RTK reference on land?
Yes. Basically, all of our antennas, because they are just RF antennas, they could work as RTK. They could work in an RTK system. So obviously the selection of the antenna for the base and the selection of the antenna for the rover would be important. The base, you'd want to get the best precision possible, so you might use something like a Veris choke at the highest end, Veriphase, Veristar. Sometimes, for maybe low-cost solutions, you could use a patch like a 3972, a TW3972 patch antenna as a base. And then in the rover, you would select whatever works best for your whatever the rover is. So like a drone or a tractor or any of those vehicles, you'd select the antenna that is best suited for the application. There's a variety of that. But in short, yes.
Beautiful, thank you, Joe. The follow-up question here is: great presentation. How much are your filters adaptive to the changing conditions? For example, interference, multipath.
That's a good question. And I think it raises a few questions in my mind, but I think to answer that first, well, it depends on what is meant by adaptive. So in terms of the filtering, well, there's a reason why there's a variety of different models out there. The main differences between the different models of the same product or family is going to be in the coverage and the filtering. So, for example, you could have an antenna that's bare bones L1, L2. Its filters cover the L1 and the L2. That's going to be the model, and that's it. Its frequency tuning will be specifically for those two frequencies. For example, in terms of like, say the Veristar, we know that there's the marine version. There's also the standard version, which is essentially the same antenna, but instead of the marine filter, it's got standard filtering that doesn't reject as strongly the SATCOM uplinks that we were mentioning before. So in adaptive, like if you're buying the product, it won't be adaptive. The filtering won't be adaptive in the field, but you could buy the correct model to suit your needs. Of course, the other one is multipath. In terms of multipath, you really you could consider, say, the SERPA. So the multipath performance of the SERPA will vary with null placement, of course, because the radiation pattern is varying while the nulls are being steered. So there will be varying performance in terms of multipath mitigation in that sense. For something like a Veristar, a Veriphase, a Verichoke, you will see that, well, the radiation pattern is static. So you'll see whatever left-hand gain you get at low elevation or below horizon, that's what you're going to get all the time. So you're looking to minimize that left-hand gain as much as possible. So a Verichoke, of course, you wouldn't put a Verichoke on like an aircraft or something like that. But a Verichoke would give you the very best multipath mitigation because the gain, the left-hand gain, even the right-hand gain at horizon and below is just minimized. Veriphase, it's a close second. And then the Veristar sort of comes in around third, where the right-hand gain is quite good, but the left-hand is also quite reduced. But you could also consider that a patch would work quite well for similar reasons. And also the helical, specifically the 3 centimeter helical, is actually quite useful for mitigating multipath for the same reason. The left-hand gain at and below horizon is actually quite low.
Excellent. Thank you, Joe, for that precise answer. I think this question is a perfect segue to the conclusion of our webinar. So as next steps, we will be sending out a thank you email. You can access the webinar, and if you have any questions or if you require further insight, please feel free to reach out to us. The contact information will be in the email. And if there are any projects that you're working on, we would love to connect and have a quick discussion and see if we are able to support you with your projects. Thank you, everyone, for your time. Thank you for your attending. Dennis, Ben, and Joe, thank you very much, and have a wonderful rest of your day.